Hello, everyone. Good morning, good afternoon, good evening. First of all, I want to make a few announcements. This is the last day of the conference. This is the opening session of the last day. I want to, first of all, thank all the presenters and participants and everyone for their positive feedback and patience. This is the first time we're putting ISF online. So this is our first virtual ISF. We're setting record high numbers in terms of registration. Today, we have 648 registrations, and the Institute had 1,264 members, both very, very high numbers. This is all thanks to to all of your contributions, presenters, participants, and of course, organizers. It's been hard work and definitely totally worth it. I want to encourage all of you to have your students to join and connect with the forecasting community, talk to your colleagues, and have them join the community and work with forecasters all over the world, right? In a few days, we'll have the wrap-up email and communication to the conference attendees. We'll wrap up the prizes, awards, and a few announcements. We'll be putting the recorded sessions online they will be available to all the members. The keynotes will be available to the public. So actually, we already uploaded the intro session and the opening keynote by Rob Hindman to YouTube. So you can watch those in case you didn't get a chance to watch the keynote live. Next year, we plan to have ISF virtual as well. We're planning a few hubs. Okay, so there will be hubs in Sydney, Australia. There will be hub in Lancaster. There will be a hub in Beijing, China. There will be a hub in Rio from South America. And we're looking for volunteers for this. So if anyone want to volunteer to host a hub in the US, let us know. We also have some plans for India. So we're also looking for volunteers for all these exciting activities. So any ideas are welcome. Please let us know, contact us. We're open to new ideas. So having said that, let's formally start the session. This keynote session, the keynote talk is given by Professor Henrik Madsen. Okay, Henrik got a PhD in statistics at the Technical University of Denmark in 1986. He's currently a professor in mathematical statistics. So his research interest is related to analysis and modeling of the stochastic dynamic systems, including signal processing, time series analysis, identification, estimation, gray box modeling, prediction, optimization, and control. So he has published hundreds of papers, more than 500 papers and 12 books. So I bet maybe most of you have read his textbook in time series analysis, among others. So today, Professor Madsen is going to give us a talk on green transition. So floor is yours, Professor Madsen.
Thanks a lot, Tao. Now you should be able to see my screen. Yes, I'll talk about forecasting for the green transition. I think this is a very, very important topic because of the increase in the CO2 content of the atmosphere. We really need to do something. And as I will argue here, forecasting is going to play a key role in the green transition. So this is an overview of my talk. I'll start saying a little bit how the situation is in Denmark and our goals. Then I will, my talk will be a combination of practical experience from doing renewable energy, wind, solar forecasting for 30 years, but also I'll also point on some more theoretical aspects here and there. So I'll start mostly with point forecasting, and I'll zoom in on something which I think is very important but partly overlooked, for instance, like adaptive forecasting, also to build in proper structure for temporal hierarchies. Then I will move into probabilistic forecast scenarios, and use of stochastic differential equation, also stochastic partial differential equation for forecasting. and zoom in on the multivariate forecasting like wind and solar and so on combined using gray box models, and also see on how forecasting can be used in control, optimal control, which will be important in the future. Denmark, in Denmark, we have the goal to be fossil free in 2050. And until now, basically, most of the intelligence has been on the, or is on the, into the production side. But of course, approaching the fossil free situation, all the fossil based generation will disappear, and we will have a weather driven energy system. So the intelligence has to move from the production side to the consumption side. And so also the forecasting techniques in the future need to be able to zoom in on smart buildings, smart districts, and things like that. And this is also something I will cover in later on in my talk. Today in Denmark, we have roughly 50% of the power of the load comes from wind, which of course is fluctuating a lot. So it is a challenge from time to time. This is just a screenshot of how it looked like a couple of days ago when I made this presentation. Sorry for the Danish here, but here the power consumption was 3,400 megawatt. Denmark is a small country, so in US there will be way higher numbers. And the wind turbines accounted for 80% of this total power. From time to time, we see that the wind power production covers 120, 130% of the needed electricity. And then, of course, we have connection to our neighboring countries. Yes, I have been working with energy forecasting, renewable forecasting for around 30 years. Our systems and our software, our methodologies are built into many technologies used, for instance, in Australia, but also in North America, Asia, and so on. I remember when I started in the early 90s together with a transmission system operator at that time, the CTO of the transmission system operator said to me, "Henrik, you don't need to worry about it. We'll never pass 5% wind power." But he was wrong in his forecast, and actually he's also shifted to the political area, so he's now in with the politics. I will not go into the details here, but the systems we have developed are in operation with all major players in Denmark and also in many other countries. We provide software engines to a lot of other systems. When you do a prediction of forecast, you need it basically from 5 minutes to 10 minutes ahead, a few hours for safe regulation of the power system and the transmission system, up to a day ahead, things like that for trading. For instance, in Denmark, we're trading on the Nordic Power Exchange, Nord Pool. But you also needed several days ahead in order for planning the operation on, for instance, combined heated power plants. We need forecasts both for single wind turbines, plants, regional and on the country level. And sometimes point forecasts are what people ask for, but more and more we see a need and for probabilistic and quantile forecast, because it has been acknowledged now that a reliable estimate of the uncertainty in the forecast is very important, and it's very useful for the planning and operations, which today more and more takes place using tools like stochastic programming and things like that. We should also be aware of that, for instance, for stochastic programming, scenarios are very useful, because scenarios can really represent the uncertainty in a very useful way, and I'll come back to that. One thing which is very important is adaptivity. And it's a fact that the total system of wind farms changes, not only because the population of wind turbine changes, but also because, for instance, the dirtiness on the blades, dirtiness on solar panels and so on, varies a lot. For instance, on wind turbines, the wind power production can go down up to 20%. And for PV panels in Saudi Arabia, the production can go down up to 60 to 70% due to dirtiness. And if then seeing a rainfall, then the blades and the PV panels might be more or less clean again, and the production goes up. And this is, of course, very complicated to model. So we need to use adaptive forecasting techniques. And another thing which should probably be mentioned here is also the roughness in the terrain, because our forecasting systems takes a met forecast as input and then provides the wind power forecast as output, and changes locally in the roughness of the terrain, trees, the drops of leaves and so on, makes a lot of difference. So they really need to be adaptive and calibrate to the actual situation. So let me just talk a little bit about adaptive forecasting and adaptive modeling. Let us just here consider a very simple linear model, which of course can be an arc model. We also met forecast as input and some of the x's here, but it can also of course be previous values of the output, which are in the x. And so this is just maybe the most simple model we can think of. And of course, the least square estimate available at time t, where we might have t observations, can of course be written like this. But what we want to do is to use such an estimation scheme and more advanced estimation schemes adaptively, so they can change to the actual situation of the blades, the PV panels, the roughness, and so on. So what we are using, or some of the most simple one we're using, is just adaptive recursive least square methods, where we are formulating this x transpose x inverse, x transpose y recursively like this. And we introduce the so-called forgetting factor, which might be time varying because a rainfall can trigger that we need to forget more than if we don't have a rainfall. And this can be reformulated if we have a large system with a lot of parameters to avoid the matrix inversion, that we can reformulate it like this. And that's normally the formulation we are using in this for this type of models. We can also consider double stochastic processes that are, again, in this simple setting, which contains, for instance, arcs models and so on. If the parameters in the armor part or the input part themselves are stochastic processes, then they can be described like a process like this. So this is a sort of hidden Markov model for the process parameters. And by using, in this, again, rather simple case, where we have a linear system, we can use ordinary Kalman filters for tracking. And we can also use Kalman filters for generating, or Kalman filter extensions to generate multi-step forecasts and uncertainties on the forecast and so on. And this can also rather easily be generalized to more complicated nonlinear models. But in that case, we need to use other higher order filtering techniques, but it's pretty straightforward. Instead of going into the detail of the more advanced stuff, I have given a reference to some of our papers related to that. First of all, my time-series book, we have 2 chapters on adaptive modeling forecasting. Then an important paper is this one, I think. This shows how we can estimate non-parametric model and semi-parametric models adaptively. And these are some of the tools we are using quite extensively in our forecasting setup. Then one of my colleagues also developed the methods for adaptive quantile regression, which is of course very useful for instance, probabilistic forecasting. And we have started more advanced hidden Markov change techniques for more advanced adaptive schemes. And lately, actually, this was a presentation yesterday. One of my PhD students, Jolafur, presented a method for adaptive temporal hierarchies where we can adjust, yeah, of course, the models adaptively also in a forecasting reconciliation situation. So let me dig into some of the practical aspects for instance, wind farm is of course a very important element in wind power forecasting. But of course, the dependency on the met forecast of wind speed and wind direction is very, very complicated, and it depends on the layout of the wind farm. It depends on the roughness in the terrain, the layout of the terrain. So most often we are using semi-parametric models like this to show the dependency on both wind speed and wind direction, so we can take into account the complicated situation with layouts of wind farms, etc. This wind power curve forecast, which takes the MET forecast as input and provides then the power curve forecast as an output, is then used in dynamical models, where this is just a very simple example of some of the dynamic models we may consider. Today the models are a little bit more advanced, but the main principles are the same. Basically, they normally have an autoregressive part, and then it has the dependency on the power curve model, and then it has some spline or seasonal behavior like this, which describes the seasonal variation we normally see also for wind. It's clear that the optimal number of terms in the model depends on the prediction horizon, and it's also clear that here we are also using adaptive schemes. So actually the parameters here varies in time in reality. This is just one example of a setup of wind power forecasting system for a particular country. This is, I will not go into the detail, but what we typically have is we have online forecasts for quite some of the wind turbines, typically the bigger wind farms, and then we only have historical readings for the rest of the wind farms, which we are then scaling up so we can get a regional forecasting or forecasting for the entire country. So it's the total setup can in some cases be rather complicated. Let me look into the more advanced, I will point forecasting, maybe just one example of that, something we considered quite, I think, 15 years ago. We discovered, after we installed one of the first offshore wind farms, that the dynamics of the wind power production was very regime-like based. Sometimes it was very volatile, and sometimes it was more static. So, so of course, this calls for a regime type of models, and we built this type of models, and what we saw is that the Markov switching autoregressive model was clearly outperforming some of the SETA model and the smooth threshold autoregressive models, and also the classical AMA model. So, so the Markov generated switching between regimes was way better than the other one. And we discovered in this project that what causes one of the most important regime shifts was rainfall. If we have a local rainfall coming, then the wind conditions changes and may shift rather rapidly. So what we installed was some radars, so we are able to predict also the regime shift for which indicates we have a change in the dynamics, and then we had even better forecasts. We also looking quite extensively into the use of temporal hierarchies, and what we have suggested, yeah, this just show a temporal hierarchy for quarterly series. It shows, I guess, what you all know after the excellent keynote by Rob. It just means that we need to reconcile the forecasts on the different levels so they are consistent, and we do this with this summation matrix. So I will do this rather quickly. What I will describe, however, is the reconciled forecast can be written like this constraint optimization problem, or it can also be written as this closed loop solution. For numerical reasons, it's very often easier to use a sort of formulation like this than we can use convex optimization. So we normally operate with this formulation, I would say. Something which is very important also, which I think has not really got enough attention, is that we need to take into account a proper description of the autocorrelation and cross-correlation structure when reconciliation are done, for instance, in a temporal hierarchy. And that's something we described and proposed in a paper from European Journal of Operational Research 2019, and the main work is done by my postdoc, Peter Nøstrup. So what has been proposed some years ago was to use diagonal weighting in the reconciliation. What we suggest is to use more full covariance scaling, but of course, when we work with temporal hierarchies and we do have a lot of levels, which we typically have, I'll come back to some practical situation, then of course it can explode. But we typically then reduce the dimension of the matrices by imposing some sort of structure on the cross and autocorrelation. Here we have a structure where we have the full autocovariance within the blocks, within the layers, different levels of the hierarchy. But here we have just assumed zero cross correlation between the blocks. That's of course just one structure, but it's anyhow better than just having a diagonal weighting. Here we have the same one as before, more or less, but we just simplified it further. So we just use a first order Markov assumption for the correlation structure, which in many cases describe most of what is needed. So then we have very few parameters. Here we have, of course, one autocorrelation parameter for each of the layers in the hierarchy. And we do it on the correlation structure and put the variances out in these matrices here. So that's how we parameterize the covariance weighting in total. We are also using, for instance, the graphical lasso, which is providing a very elegant way of parameterization. And we are estimating that the graphical lasso provides one way of estimating a sparse representation of the inverse covariance matrix by solving this penalized log likelihood function, where lambda is a parameter in the regularization, of course. Then we also consider this Senkage methods like this, where we again consider it on the correlation, because of the fact that since on different levels the variances might differ, so we typically do on the correlation level. And of course, here you can notice that if lambda is equal to 1, we have again a diagonal structure in the variance weighting, as we have seen in other papers. But if lambda is less than 1, then we have some weight on the empirical correlation matrix. Let me show one example, and again, this is from the paper we published last year. This is a case where we consider the power load in the 4 areas in Sweden, AC1 to AC4, and there we are using a Hall-Winter method to estimate the power load on all levels. And the Hall-Winter method, the double seasonal Hall-Winter method, is known to be very good for a rather good model for load forecasting. So this is a good suggestion. We don't have the trend part here because in the load we typically don't see the trend, but except from that, it's a double seasonal Hall-Winter method. These are the base forecast, or at least some of the base forecasts, the daily, 6 hourly, and hourly. We do also have 12 hourly and 8 hourly and 3 and 4, 3 and 2, but I'm not showing them here. I don't think we'll go into detail just to have the numbers. But here we see the improvements which we obtained with, yeah, I mentioned some of the structures, but there are also more here. We can see that if we consider the daily forecast, we got improvements up to, yeah, 50% in RMC, both in sample and actually the same, more or less the same out of sample. And if we then zoom in at the lowest level, the hourly forecast, we got forecast maybe typically improvements up to 20 to 30%, I would say, basically both in sample and out of sample. But I think this structure, to build in structures of the weighting and to penalize the structure, so we are able to work with a lot of hierarchies without having problems, facing problem with inverting a 1 million by 1 million matrix, as mentioned in Rob's presentation. That's gives a very powerful method for actually operating with a lot of hierarchies. And of course, the idea about using forecast reconciliation is brilliant, and it gives us a lot of improvements, as you can see also from these cases. So maybe the main message here is we should really take into account proper auto and cross correlation structure, and we should really try to reduce the dimension of this important weight matrix at the same time. And we are working also on new methods for doing that, which looks very promising. And it's clear that another thing which I should probably mention here is that you might think that you can just throw in any forecast on the different levels and so on, but it is actually advantageous to have a really state-of-the-art forecast at some of the levels. So it pays off to have a good MET forecast and a really state-of-the-art classical forecast system. But of course, you should then later on combine it with for instance, the temporal hierarchies. Let us now look into more advanced stuff like spatiotemporal forecasts. This is just a situation which shows the improvements in the forecast in RMSE. If we, when we do the forecast for this area, then consider the neighboring areas. So we take spatiotemporal dependencies into account. And we can see that since the wind normally in Denmark comes from the west or southwest, we get the biggest improvement on the eastern parts, because when we can discover the errors, phase errors and so on in the MET forecast already in the western part, and then we can take that into account in the more eastern part of the country. So it gives good improvements, and this should of course be used. Another thing which is also just a practical information, which I guess many of you know, but just in case, it's very important, as we see, to use several MET forecasts as input, because each system has their own priorities, and it's very good to use these forecast combinations and so on to find the best input and combination at each point in time. And we see typically for improvement of 10 to 15% in the accuracy of these point predictions. So it's very important with more than one MET forecast. Then I will dig into probabilistic forecasting now. What we are considering depends on the situation and what the system operator or balance responsible party actually asks for. But we sometimes use a ensemble-based forecast where we use meta-example as input. But here we have not corrected them so they span the correct probabilities. But here shows what happens after correction, and that's a really simple way of doing it, and then it's useful. Then we also using quantile regression, or more precisely adaptive quantile regression. But today, I think that use of stochastic differential equation and partially observed stochastic differential equation, what we call gray box models, is what provides the state-of-the-art forecast. I will come back to that, of course. So quantile regression, that's a model for the quantile. It's typically formulated as an additive model. And this shows the effect of some of the explanatory variables. This one shows, for instance, that the power forecast itself is very important in describing the uncertainty. And as you can imagine, when the wind the wind power forecast is around the areas where the power curve is more steep, then of course we also get more uncertainty. Whereas if we have very high wind where the wind turbine by themselves control the wind power output, so it's more or less constant, then the uncertainty collapse again. So this is what we see in this curve here. Here it shows that when the wind comes from the west and southwest, the uncertainty is way higher than when it comes from the east. And I guess experts in meteorology can explain me why that's the case, but that's at least what we see. This is one example of probabilistic forecasting. One thing we should, of course, notice is that, and that's also why I was a little bit afraid when I first met with our system operator in the early 90s. This is clearly non-Gaussian because for linear time series and Gaussian processes, the uncertainty will increase with the horizon, and also the uncertainty will be independent of the process itself, but only be dependent on the horizon. But for wind and solar, and I think this is not the case. The uncertainty can go up and it can go down again. So that's very important to notice. One thing we should take into account is also that the correlation, here you see what we observe later on, this correlation is not really described. And that has, of course, to be described in order to really take the correct decision. That can be described, for instance, by a correlation matrix after some proper transformations. So we can use some of these Gaussian born methods like a covariance matrix. This shows how the correlation between errors on 25 hours or 28 hours are correlated to a 12-hour forecast here, but less correlated with some others. And then we can build scenarios based on this. But the scenarios, this shows one example for several days with correct scenarios or reasonably correct scenarios, where here we have forgotten to take into account this autocorrelation of the forecast errors. So this is, of course, very important to do that. One thing we should notice here, and that's where the stochastic differential equation becomes important. If this correlation structure this of course changes with time in reality, but stochastic differential equation can describe this by time varying parameters in the diffusion term. So using that, we can describe how it varies, and we can also avoid this transformation needed normally to use this type of Gaussian techniques like such a correlation structure. So we are more and more looking into the use of stochastic differential equations. And this is just a simple setup. Later on, we'll see a more complicated setup. But what it shows is we take a typical state-of-the-art wind power forecast, and then we model the errors from this state-of-the-art wind power forecast tool using stochastic differential equations. And this is just, in reality, it's a bit more complicated than this, and you can consult some of the papers which I have at the end. This shows then how we can describe the uncertainties using stochastic differential equations for a particular wind farm. It also shows that the CRPS score for this model and also the total score, multivariate score, the energy score, is way better than some other state-of-the-art methods which could describe phenomena like this. Yeah, maybe I'll skip this. This just shows how the correlation structure, this is the same as the covariance matrix we saw before, but now these are built based on the stochastic differential equations. So this shows how these regularly can vary in time, and this is, of course, extremely important in many cases. We need also to consider the space-temporal dependencies. So the autocorrelation in one region is not enough. We need also to see the cross-correlation between the different areas. And in order to do that, we need space-time matrices where this correlation matrix for one block is here, but then we need to describe the cross correlation between the different zones. This can be done like this, but it's even better to consider the precision matrix, because then we typically just need a few parameters to describe this space-time correlationship. Instead, another thing which we think is very powerful is to use stochastic partial differential equation. And now I'll just zoom in on a particular wind farm from a little bit north of San Diego, where I do space-time forecasting for this red area with 5 by 14 inverters, because when a cloud goes over this terrain, it can really have a lot of dramatic influence, and so it would be good to make very short-term, very accurate forecasts. And this can then be modeled again using stochastic differential equations, but formulated over this grid. And if we normalize it in a proper way, then we can write it as a stochastic differential equation. I don't think this overview lecture will really go into the details, but we can see that we really, these are the different horizons, and we can see that it really outperforms an autoregressive model, which normally is used in this very short-term forecasting. These are some of the papers we have drafted on the use of SDEs for forecasting, so you can dig into some of the details. Solar power forecasting is, until now, I have mostly considered wind power. But solar power forecasting, for that we are more or less doing it the same way. But what we typically do is we estimate the clear sky solar radiation as a function of the day in the year. So this is summertime, and here we have the time of the day and night. And of course in the winter, and again this is Denmark, most of the data here is from Denmark. So in Denmark, on this high latitude, the day is very short at winter time, but of course long in the summertime. So this here for this site, we can estimate how the clear sky solar radiation is. And then we can model the atmospheric transmittance, how the water content and dust in the atmosphere, and also in particular the influence of clouds, which is very important, of course, how it varies dynamically using a dynamical model like Markov processes and things like that. So this picture is very important. And combined with these dynamical models, we can then get forecasts like this for different dates. Let us now at the end consider the use of stochastic differential equation formulated as gray box models, which I think is really state of the art. Gray box models are models which bridges the gap between black box model, like a neural networks model, machine learning model, and maybe also ARCS model is really black, and models which are based on first principles and physics. It has several advantages because we can draw in information from physics, and then we can use statistics to upgrade the model until we have a reasonable model. We have developed a tool for doing that here at D2 Compute, and you can it's free, so you can download it for this from this homepage. The stochastic differential equation in the gray box models are used to describe the dynamics, and it has the drift term and the diffusion term. And it's a sort of hidden Markov process because we only measure YT. And let me see one example of the use of this, where we consider the forecasting for a smart building, which has a heat pump, and it has also an electrical heating system. And here, the model for the building turns out, in this case, to be a linear gray box model. So this is basically a rather simple model. But if we look at the disturbance model, or the model for the weather forecast, it looks like this. And again, I'll not look into the details, but the solar radiation is this part here. This is the net radiation, and this is the air temperature. And this we typically don't measure directly. We only have a few measurements of the global radiation and outdoor air temperature. If we zoom in on the model for instance, the outdoor air temperature, then it looks like this. So this is again a stochastic differential equation, which in Denmark, which is surrounded by sea, then we need a slow dynamics with the sea, and then the more fast dynamics, the thermal mass of the countryside or the land area. So these second order models turn out to be good for describing the air temperature, to forecast the air temperature in Denmark, and it takes the net radiation, the net as an input. Net radiation is the difference between the long wave and the short wave radiation. So it describes the radiative balance totally at the surface layer level. Then we use this in an optimal control problem for really for the smart building. And here we have an element which minimizes the cost of the use of electricity, and then a term which penalizes when we exceed the constraints which we typically have in this type of control. And as I said, the model for the building is typically a linear, or in this case, it's a linear model, so it's simply written like this in discrete time. And in discrete time, and we are using discrete time normally when we consider control, because that's normally the control action is valid for the next 5 minutes or in discrete time steps. So this is not formulated in continuous time like in discrete time. The forecast, advanced forecast for the MET forecast, the outdoor air temperature, solar radiation, and so on, enters the system here. So this is coming from this system here. This is then built into a system which we are used to set up to optimally control smart buildings, which then do these forecasts of the disturbances, which is solar radiation, wind speed, and outdoor air temperature and things like that. Let me look into some results here from a simulation over 7 months, but this is way, as far as I remember, only, yeah, that's 14 days. And here we have a building which has electrical heaters. Here we have heat pumps. Here we have heat pumps and electrical heaters, and here we have heat pumps, electrical heat, and coolers. Electrical heaters are very fast, so here we typically don't really violate the constraints. For the heat pumps, we can violate the constraints, in particular if we don't use this advanced forecast. But if we are using the advanced forecast, using the gray box models, which we do in our setting here, then we are doing pretty well. And also for the more complicated situation where we both have coolers, electrical heaters, and heat pumps. When it comes to electricity cost savings, this is perfect forecast. So here we have assumed what we know later on about the weather. Here we have the forecast normally used in control, but we can see our gray box forecast techniques are pretty close to the perfect forecasting for this type of control problems, at least. In order to draw more generic conclusions, we need to further studies. We can also see when the violation of the constraints with the advanced forecasting techniques using gray box models, we are, of course, not as good as perfect forecast, but we are way better than what is normally used in this type of control of smart buildings. So let me conclude by some few remarks on what we have learned. We think the models, the forecast should be adaptive. A lot of things should calls for adaptivity, also in forecasting hierarchies. So that's very important. We should also really take into account proper estimates for the uncertainties, and this can be provided by the stochastic differential equations like shown in this slide. We should also use more than just a single MET provider. That's very, very important because it really pays off. And we should, as we showed with some example at the end here, take into account cross dependencies by the different components which influences, for instance, the smart buildings. And that can also be done by considering the stochastic differential equations formulated using a gray box model. And by doing this, if we have the stochastic differential equation, then we can generate scenarios, we can generate the sequence of conditional densities, and we can do more or less whatever we want. And we can answer all interesting questions. For instance, what is the probability of an increase in wind power production of more than 50% of installed power over the next 2 hours and things like that. That can be answered rather precisely, or in a rather good way, I would say. Everything is a common way uncertainty here, of course. Some of these topics on gray box modeling and advanced forecasting will be covered in the summer school next week, and I think the material will be uploaded later on also. So I want to thank my former and present or actual PhD postdocs here. Here are some of the contributors to these slides, which are in my team or have been in my team for a longer period. So thanks a lot for your attention.
Thank you, Henrik. I want to open the floor to the audience. Anyone have any questions? You can either type in the chat box, or you can type them in the Q&A window, or if you want to, you can raise your hand, and then I can mute you. Any questions from the audience? Oh, I got one. Okay. Okay, so this is from Tess. The question is, are the forecasts used in the optimal control problem point forecast or probabilistic forecast?
Yeah, it depends on the controller. If we are just using a model predictive control, what we're doing here, then we typically use just a point forecast. But in the more advanced LQG controllers, which takes into account stochasticity, we are of course using the uncertainty. And of course, since we are using stochastic differential equation, we can generate both conditional means, point forecast, second order moments, variances, and screwed distribution and scenarios, whatever. So I think the forecasting mechanism we have can generate what you need for the actual control problem.
So any other questions? Any other questions? You can either type in the Q&A window or in the chat box. Okay, so I just got another question from Anton. How these methods of point forecast, load forecast extra are comparing with neural networks? Yeah, I guess the question was about comparison, how these methods comparing with neural nets.
Yeah, here I decided not really to compare with neural networks, because I want to highlight the importance of adaptivity and also the importance of being able to include any physical knowledge. But it's clear that sometimes we are using also machine learning, neural networks and things like that. But I would say for this type of systems, adaptivity and then not too many parameters, which is somehow closely linked to be able to use efficient adaptive schemes, are very important. So I think that for this type of methodologies, I would stick to a more white than black box type of forecasting technique, I would say. But typically we compare with machine learning techniques and so on, and see what's the best.
All right, so here's a follow-up question regarding this neural nets machine learning. So the next question was from Mehdi. Can you please comment on deep learning and machine learning models in renewable energies? Have they been successful? I assume this is about renewable energy forecasting.
Yeah, I guess. Yeah, we have used it also, and we have also found it very useful in some settings. And one setting I can mention now is a forecast for PV production in Japan. They have a lot of PV in Japan. Maybe some of you are from there. And we have been asked to set up a PV forecasting system. And due to the different tilting of the PV panels and shading and things like that, we found the use of machine learning very, very useful, because then we could really train the different forecasts for the different sites and also see how the sites relate using machine learning techniques. and we have published papers on that as well. But I didn't find time to cover it here. So I think you should definitely consider machine learning also.
All right, so next question is from Nichols. So he's a fan of temporal hierarchies. Right? His
Yes.
question was, do you see with advancements in estimation approaches and machine learning a translation to more conventional multivariate models for the same style of modeling? He said in his personal experience, although you can squeeze a similar performance, I always find it to be rather cumbersome. Any views on the spatial temporal systems that you have worked with?
I think the space, the temporal or the temporal hierarchies and so on provides a very powerful methods. But I think also when you do these hierarchies, I think it's good to use different forecasting techniques on different hierarchies and just combine it. At least we find it very useful. But the lessons we have learned it also at some of the levels. It's also good to have a state-of-the-art forecasting technique designed for one level, which are more in line with what I showed in the beginning of my presentation. But then, of course, you should combine it with some. You could use some rather simple forecasting technique on some levels of the hierarchy. That's something we do also, and I also think some of the presentations we presented yesterday used some rather simple machine learning type of forecast on some of the levels of the hierarchy.
All right, thank you, thank you. So next question is from Yi Li. So the question is, how do you justify the forecast quality from METs? When combining models, do you put more weights on METs that are consistently better? So basically, this is about forecast combination. How do you combine different forecasts from MET providers?
Simply I let the data speak. Like in forecast reconciliation, combined forecasting, forecast reconciliation is pretty much the same. So I simply estimate which weight is the best. And something which can be tricky is that some MET forecasts are rather bad when we have convective phenomena or convective rainfalls and things like that, or instability in the atmosphere. So sometimes we parameterize the forecast combination as a function of some of the physical parameters, like the instability of the atmosphere. So I don't know if that was an answer actually, but
Thank you, Henrik. The next one, I think you have talked about this at the beginning, so about adaptivity. So the question was also from Anton. The question, could you please expand on the notion of adaptivity? What do you mean by adaptivity?
I mean that the model I have now for instance, for wind power forecast is should be optimal for the states of the wind turbines I have in my population. And they might be more or less dirty. We might have a certain population of wind turbines. And if I consider a forecast for Denmark, which we provide for our system operator, then of course this population of wind turbines changes from day to day. And we need a model which can automatically adapt to that. And also, since I'm using MET forecast as input to my forecast system, I need to take into account also changes in the roughness in the terrain. If a farmer harvests their corn and so on, then of course the roughness changes. And this can be done more or less, this can be handled by adaptive forecasting methods.
Thank you. I guess for the interest of time, I will just ask one last question. This is from Mehdi Fadi. The question is, could you please suggest some future research in energy analytics? Well, it's a big area. So any suggestion from you, Henrik, to
But I think this what we have studied lately, the use of gray box modeling and forecasting seems to be a very, very powerful technique. So this is something which we plan on to consider further. So the use of stochastic differential equation, but also combined with hierarchies and machine learning and yes. But we saw a lot of benefits from this in the power of stochastic differential equations in general. That's really gives us all the tools we want for forecasting. But that needs to be further. That needs to be further expanded on. For instance, adaptivity in this type of models is still something where we don't have the best solutions yet, as far as I see it.
Thank you, Henrik, for the great keynote. Thank you, everyone, for participating in this keynote session. This is the top of the hour, so we have 2 more sessions to go for the ISF. So please give a round of applause to Henrik. All right, I will see you guys later in the other sessions. All right, bye.